Okay, so in the previous video, we had the Lagrangian phi dot squared over 2 minus 1/2 d phi dx squared minus a constant times phi squared. And we argued that we could recover this term as a result of a coupling between isolated harmonic oscillators and taking the continuum limit. We didn't do a great job of arguing for this term, so let's sort of review that argument and then make some concluding statements. So we argued that as phi goes to 0, right? So we had two masses. This is the coupling between the two, and this is the distance between the two in the horizontal direction. And then we had a phi, and so this is x squared plus phi squared. And so that's the distance between them here. And as we make small displacements in the vertical direction, this looks like, we said this looks like phi squared over 2 x squared. And then we were very casual here. We said this goes like phi squared. Really what we wanted to say was that this goes like phi squared over x squared, apart from that constant. And of course we argued a way for this term. It doesn't affect the Lagrangian. But this is the key for understanding how we get a term like this. And the way to do this is to think of, in the continuum limit, we're making both the distance in the horizontal direction go to 0, and the distance, we want small little displacements in the vertical for phi direction. And so let's say in the continuum limit, right, so we have a collection of simple harmonic oscillators, a couple simple harmonic oscillators, which in the continuum limit means that x is going to 0, but phi also goes to 0, and so phi squared over x squared looks like the d phi by dx squared, right? So we recover the definition of derivative, in this case derivative squared. And so we should be thinking of, how do we say this? So a continuous collection, something that we should refer to as a field of coupled simple harmonic oscillators, is where quantum mechanics and special relativity come together. This is somewhat of a strange idea, right? We have to make this kind of object. Let's displace one of these, right? These are the limit of this kind of a thing, collection of masses connected by strings that can oscillate up and down, and they are coupled. And whatever that thing becomes, it usually is referred to as a mattress, especially when we have three-dimensional, so x and y, right, where that becomes a del phi squared. That is the object that you have to deal with when we're combining quantum physics and special relativity.